This is the free response section of the Chapter 7 test, and this is number 11. So it tells us in this problem that the weight of the eggs produced by a certain breed of hen or chicken is normally distributed with a mean of 65 grams and a standard deviation of 5 grams. So I'm just going to make a note here that these eggs are normal with a mean of 65 and a standard deviation of 5. Part A asks me to calculate the probability that a randomly selected egg weighs between 62.5 and 68.75 grams. So since I know that it's normal, I might draw a nice picture here. And the mean is 65 and the standard deviation is 5. So this would be 70, here would be 60, and what I'm looking for is the probability that a single egg weighs between 62.5, which is, I don't know, maybe about right here, and 68.75. So, I don't know, something less than 1 standard deviation away from the mean, both below and above. Okay, so I wanted to see a picture like this where you were drawing and shading in the correct area. And we actually need to find 2 z-scores here. We need to find the first z-score and the second z-score, and then we're going to calculate the probability that z falls in between those 2 values. So my first z-score would be 60 minus 65 divided by my standard deviation, or excuse me, not 60, but 62.5 is that first value. 62.5 minus the mean, 65, divided by the standard deviation, which is 5. So 62.5 minus 65 is negative 3.75, or excuse me, negative 2.5. And negative 2.5 divided by 5 is negative 0.5. So my second z-score then is found by the other observation, 68.75 minus 65 divided by 5. And that gives me negative 3.75 divided by 5, and that's equal to 0.75. Sorry, that's not negative, that's positive. So now what I want is the probability that z is between negative 0.5 and positive 0.75, and that corresponds to this area that I've shaded in here. Half a standard deviation below, up to 3/4 of a standard deviation above. This I'm going to do on my calculator, and we're going to do the normal CDF. My lower bound is negative 0.5. My upper bound, in this case, since I'm doing a between, is 0.75. My mean, that's like high, I don't think about it that way. My mean is 0 because I've standardized the scores, and my standard deviation is 1 because I've standardized the scores. And when I do all that, that probability is about 0.4649, and that looks right according to what I've shaded on the screen. Now, this is a single randomly selected egg, so this is just the normal distribution for the entire population. But in part B, it changes a little bit because now I'm looking at a carton of eggs. And we're going to think about that carton of eggs as a sample of size 12. Now we want to calculate the probability that the average weight of those eggs in a carton falls between 62.5 and 68.5. So now what we're working with, instead of a single sample from the population, now we're looking at the sampling distribution. If I've got 12 eggs, then I would expect the standard deviation of the average of those 12 eggs to decrease quite a bit. So, oh my gosh, there's my normal curve. Not very well drawn. The mean is still 65, but now my standard deviation of all of these is going to be 5 divided by the square root of the sample size, or divided by the square root of 12. And that's about 1.44. So if we think about 1.44 as the standard deviation, that means this value here is about 66.4, and one standard deviation below is, let's see, 65, 64, 63.6. So the two observations that I was concerned about are much farther away from the mean. So here's 62.5 way over here, and here's 68.75 is way over here. So the probability that I'm going to get an average in between those two should be much bigger. So we still follow the same process of finding the two z-scores. So my first z-score would be 62.5 minus 65, but now we're going to divide by that new standard deviation of about 1.44, and that gives me a z-score of negative 1.73. My second z-score, I'm going to take 68.75 minus 65, divide that by my new standard deviation, 1.44, and I get about 2.598. So now I'm going to calculate the probability that z is between negative 1.73 and 2.598. And again, that's a normal CDF calculation, and we're going to go from negative 1.73, that's my low, up to about 2.598, that's my high, my mean is 0, and my standard deviation is 1. And when I do that on my calculator, I should get a probability of about 0.9535. And again, comparing that to my picture, that makes sense because look at that huge area that I've shaded in. Alright, and in part C, did we need to know that the population distribution of egg weights was normal in order to complete parts A or B? And the correct answer is yes. Okay, because is the important part here. In part A, we were looking at a single sample, so we needed to know that the population was normal in order to do the calculation. And that probability. Okay? However, in part B, while we're doing a sampling distribution, the sample size is still pretty small. So that means that it probably was not big enough to normalize the sampling distribution if the population hadn't been normal to begin with. So it wasn't, the sample size n was not large enough to ensure that the sampling distribution, let's see, what was I saying? Large enough to ensure that the sampling distribution, or the distribution of all my x bars, would be normal. Alright, so that's it for number 11.